Fantastic. Okay. Griffin Bishop, everyone. Yay.
Hi. Yeah, I'm Griffin, and I'm going to be talking about all types of retrieval today. A little bit about me. I did some research on self-supervised representation learning for computer vision for my master's degree, and then I did ML at Amazon and a couple startups since then. And last year I started a startup called Knowledge Work, which is a desktop application which takes notes on your workday, including your meetings and your deep work sessions, like if you're coding. And we built a bunch of different retrieval systems that allow you to ask really complicated and interesting questions and potentially automate things based off of your entire corpus of work activity, and over weeks, months, potentially even years, if we last long enough. So we learned a ton about how to build high quality retrieval in building this, and I'm really excited to share it with you. So first of all, what is retrieval with respect to large language model systems? And in particular, I'm going to talk about the application layer. So if you're building, the best example would be a user-facing chatbot. How do you do retrieval? Why do you do retrieval? But there is a lot of retrieval that happens on purely back-end services as well. But I'm mostly going to talk about user-facing kind of chatbots and things like that. So imagine you're building a customer service support chatbot, and the user is asking a question about the return policy. If you just gave that question to the large language model prompt without putting your return policy in, you're going to get all sorts of problems. You're going to get hallucinations. You might get a rejection from the model. That's if you're lucky. And also, it's why is the user coming to your service? They're probably not coming to your service for your prompts. Like a lot of people think they're the incredible context prompt engineers, but usually they're coming to your service because you have some non-public information that you're going to put into the prompt that allows the LLM to do what the user wants. So here we have, basically retrieval is the process by which we go through our corpus of documents or data about the user potentially that we've collected, and we decide what to include in the prompt that will enable the LLM to perform its task. And if you don't do this right, the number one thing you're going to have is hallucination, and it's going to be super weird, and it's going to be really hard to debug. So most of what we figured out is actually more of DevOps, as in what are the best types of systems that are most amenable to debugging and actually improving over time versus just building once? Because I think at the start of this, a lot of people just focus on how do we make something that works, but we want something that the team will be able to improve upon systematically over time. So the question is, why do we need to do retrieval in the first place? Why don't we just throw those policy documents I had in the slide before? Why don't we just throw all this return policy, shipping policy, privacy policy? Why don't we throw all of it into the large language model prompt and just see what happens? And to be honest, I think you should probably start there. I think that's actually a really good idea. And in a lot of cases, I think you'd be surprised at how well it handles it. Basically, if all of your documents that you're talking about are under 40,000 tokens, modern LLMs can actually handle that extremely well. But usually, when you're building something like this, you have a lot more than that. You have lots of data per customer, and that's when you need to get more complicated. The other thing is, you'll quickly find out that it's way more expensive to do multi-turn conversations with 40,000 tokens just to start, and it takes longer. So the more tokens you put in, the more time per token it takes to produce a result. So you want to optimize that there. But actually, I would say those aren't. Most of the people I've worked with, that's not actually the main concern. They're not concerned as much with cost or latency, and they're really concerned with the quality of the output. And I think that'll continue to be true for a while when you're building in the application layer. for most companies and startups. But what is a really big problem is context rot. And this is kind of a new term that I really like, which is the observation that as you add more and more irrelevant information, there's some, you're trying to search for a needle in a haystack, and you have the return policy in some place, and you have a bunch of other information as well. As you add more irrelevant information for the LLM to kind of discern, the more degraded the output quality will be. So this is a real problem. This is one that, even as the models get more intelligent, their capacity to withstand this problem won't necessarily keep up with that. And to illustrate it, I think it's really interesting that I don't think this is just a large language model problem. I think this is actually a problem with human-like cognition in general, and there's a bunch of research that supports this. So here's an example I found. Actually, this question is really, really unintuitive if you'd like to try it. But on the left, we have version A, which is there's no irrelevant information added. There's only the information that is required to solve this problem. On the right, it's the same problem, but there's a lot of random numbers and information that you kind of have to figure out, okay, is this related? Obviously, the stuff that is relevant is just bolded. So, but yeah, when psychologists show this thing on the right to humans, they do significantly worse. This is already a hard problem to start with, and they do way worse. So I think this is like a natural problem that in general, when you're engineering, the more that we can put only the relevant items in the context, that's just kind of a fundamentally you're going to have a more successful product. So that brings me to the first method for retrieval that I would say this is still the most popular method, although there's cracks forming, and I'm a little bit biased against it for reasons I'll explain in a second. But it's been the most important retrieval method, the most common retrieval method in the application layer so far, until pretty recently. So what is an embedding? An embedding is a machine learning model that has been trained to take text input strings and map each of them to a very high dimensional vector, often 16,000 dimensions, so 16,000 floats. But it has really useful properties. It has really useful properties as in two vectors are related to each other algebraically, in the same way that the text is related to the other text input semantically. And how that's useful to us is that two inputs that have the same meaning, but they're stated in different literal vocabulary, those will map to a very, very similar vector. So that's super, super useful. That means if we're, that's extremely useful. And similarity in terms of cosine similarity in particular. So in the example, you can see like the cat sat on the mat, that is saying the same thing as the feline sat on a rug, or rested on a rug, but the vocabulary is slightly different. So that's kind of hard to, if you're just going to do textual search to find a similar one, that would be difficult. But the vector, if you were to do a cosine similarity search, you would be presented immediately with that result. Whereas the third example, stock prices rose sharply, you can see that is, the vector's significantly different. So that's a super useful property that makes this whole embedding RAG system work. So how does it work with embeddings? We take all our documents, so like all those policy documents, so maybe even one document is too big to put into the LLM. So if that's the case, we have some chunking heuristics. So we figured out a way to cut the document into nicely sized pieces. For each chunk, we calculate the embedding, and we store a mapping from every vector that we've calculated to the corresponding chunk, or probably chunk ID in your database. And there's a bunch of tooling that makes this really, really easy, like Pinecone, there's a Postgres extension. but yeah, this is just the concept. So that is all ahead of time. So you have your corpus of data, you chunk it, you embed it, you store the mapping in a database. That happens in the setup phase, and every time you add new data, you also need to do that and add to your database. Then when at inference time, or when the user enters their message, you do a similar thing. You calculate the embedding of their message, and you calculate the cosine similarity from that vector to every vector that is in your database. Then you sort that, and you take the top, k, and usually it's like 5 or 10 examples, and you pray that the answer to the user's question is in that corpus, or in the 5 chunks that you return. In reality, you don't actually have to calculate this. This is extremely efficient. You don't. There's clustering algorithms that enable you to, effectively compare the embedded user message to your entire corpus without actually, calculating the cosine similarity for everything in your database. So this can be very, very efficient, very, very fast, and very, very cheap. That's kind of the best part of this embedding RAG. So this is just to show there's the setup phase, indexing, calculating the embeddings, and then when that's different from when you're actually running your application and the users enter something. So embedding is great because it's so low cost and it's so efficient. But there's a couple things I really, really don't like about it. The biggest thing is that it's not transparent what's happening. It's hard to explain and reason about why, if something goes wrong, I'm looking at a trace, I'm seeing, oh, there's 5 chunks returned and the answer wasn't returned. It's really hard for me to look at that and be like, why didn't it put in this, chunk over the other? Like the embedding model, that calculation is very inscrutable. So that just makes for, a lot of difficulty. So that's probably the biggest problem with this. The other thing that is really difficult, and I really don't like about the embedding method, is the chunking. Chunking is so important to the success of embedding RAG, and there's so many different ways to do it, and there's no one-size-fits-all solution. It's also, the more structured your data is, the more assumptions you can make about what the chunks should be. So that can help, but if you do it wrong, there's a lot of ways it can fail, and I guarantee you're gonna see all of them. So this is an example. So let's say we have a parental leave policy document on the left there. To answer this question, we actually need we need 2 of the chunks in this. Like, let's say we're going to divide by chunks by section. We actually need both of those in order to answer this question effectively. But if, let's say we chunked and we said we're going to chunk every paragraph or we're going to chunk every section, it's totally possible that only one of these would hit the similarity threshold and the other one would not. And we wouldn't know. Like, if I went to go debug this, that wouldn't be obvious. Another problem that can happen is, and this one I think is actually much more fundamental. The other one was a problem if you chunk incorrectly. This one I think is actually more worrying, which is that your user isn't an expert. Like, they're probably coming to you to ask a question about the return policy or the parental leave policy because maybe they don't, they're not an expert at what that is. They might not know the vocabulary that's required to ask the question effectively. So, oftentimes, you get questions like this that are describing, symptoms that they're, having, like if it was like a medical system. So you can't expect your user to frame the question in a way that is similar to how the answer is stated in your data. And there's a lot of attempts to kind of fix this problem. For example, one of them is there's a method to calculate a bias matrix, or to train a bias matrix against your data and the potential questions that you could ask. And the bias matrix tries to kind of transform the input vector to look a little bit more like an answer vector. But I would say all that method and all the methods like that, I would say they feel very, very hacky, and they're not great. This is probably the most common problem, actually, which is that you're likely to, when you're looking at, okay, why didn't this work? You're likely to see that you passed a chunk to the model that referred to other parts of the document. It referred to concepts that it would, other concepts that the user would know about or that are required to answer the question, but that don't occur in just this chunk or any of the chunks that were returned. So this is actually really nefarious because the LLM will almost certainly hallucinate. It will pretend to know what the things that you've referenced in the chunks that you gave it are, even though it totally doesn't understand. So this is probably, when people talk about hallucination with embeddings, this is probably the most common cause of that. Yeah. So why, if there's all these problems with it, why is it so damn popular? It's really, really cheap and it's really, really fast. And it's especially in terms of like the ratio of the cost to the embedding solution to large language models. That basically in 2022, that was so astronomically different. It was so much more expensive to do a large language model query that you just wouldn't even consider using large language models as part of the retrieval system. That calculus has completely changed, and that has opened up the doors for the next two methods that I'm going to talk about. But to kind of illustrate this, the best example of a system that has completely changed their tune, that used to be completely embedding based, and now it's not embedding based, would be code-based question answering. So I feel like everyone's probably used, probably in the past year or so at least, some sort of tool like Claude Code or Codex that allows you to say, oh, how does the authentication system work in this code base? Back in 2022, those tools used embeddings primarily, and they didn't use the agentic solutions that everyone uses now. So in 2022, I had a VS Code extension that indexed my whole code base, every function with an embedding, every file, and typed in natural language, and it did this whole process. And it was okay. It was actually pretty good, but it had all the problems that I just described to you. And there's a reason that I think probably most people in this room did not have that VS Code extension. So that kind of that used to be kind of the state of the art for code-based question answering, and now it's completely dominated by agentic methods. So with instead of using embeddings to search through and hope that the most similar embedding to the user's query has the answer in it that they're looking for, we can use reasoning. So this just makes a ton of sense. If you have a highly structured data that you're asking questions about, agentic methods can work extremely well right out of the box with just a few simple tools. So, for example, for code-based QA, if you just give it the ability to list files, you don't even need like the Claude.md, and it can do really well. List files and just read and grep. You only need 3 tools, and you can get amazing performance. By the agent essentially treats the code repository like a graph, where each symbol is a potential edge on the graph, and it traverses through. And when it decides to, it has completed the research, then it can respond. And this is this totally blew away the embedding based methods for code bases of even very large size code bases. So yeah, this is probably the best comparison is something that has completely changed its tune. I would say this is the first example, and we're probably going to see a lot more into this trend. Because embeddings are so inscrutable and hard to work with, it would be my bet. Versus agentic traversal. the fact that when something goes wrong, and with code base, it's pretty much a solved problem. But if you're implementing a system like this, and it's not giving you the answers that you want, and you go to debug it, it's actually totally reasonable to debug this. You can see what tools were called, you can see what decisions it made. That's way better, and it will allow you to be confident in your iteration, and you'll totally end up at a much better place in a couple months than if you bank everything on embeddings, depending on the data, of course. The main issue with this is that it requires something that's highly organized and highly structured. So code has to be highly organized. Some companies it's not, some companies it is, but it should be. In order for humans to use it, it has to be organized. So therefore, agents can it's the same stuff. They can use the same tools. So that's a drawback as well, though, because if your data source doesn't have high natural structure, then you can't do this. At Knowledge Work, my startup, our problem resembles that. We have a lot of data, we have a lot of recordings of work sessions and meetings, and we need to answer questions that could possibly the structure that we have is basically the time at which a meeting happened, for example. So if you ask a question, what was the decision from the meeting last Tuesday at 1 p.m., then we're good. But if you have any question that's not indexed by time, it's not going to work. You're gonna ask about what did we do? What did we decide about the authentication system? Now we have to search every single meeting. So the question is, when you don't have this really nice inherent structure, what do you do? And the answer is you can use large language models to create that structure for you automatically, usually on a per user basis. And this is formally referred to as graph RAG. And I don't know if I said it, but RAG stands for Retrieval Augmented Generation, which basically is a fancy way of saying finding something and putting it in the large language model prompt. So the graph RAG method essentially says we have a corpus of data to start with, and we have new data being added to the system every so often. So whenever we add data, we need to extract knowledge graph entities, relationships, and statements about those entities, and reconcile those new updates against the existing data structure. Large language models are extremely good at this. This is a very native thing for them to do, pretty much since the beginning, which is really incredible. But essentially, so you have one agent that is the kind of ingestion agent, and it has tools like create entity, update entity, stuff like that. And so this is a graph where the entities are the nodes and the relationships are the edges. And then it's really important that for every update you make to this data structure, you include a link or a reference to the document or piece of data that caused you to make that change. And with that, you have a really, really powerful, really, really flexible representation of your data that also serves as a great index. So you guys have all used a knowledge graph before. Wikipedia is probably the most well-known knowledge graph. It's a knowledge graph in which each page can be considered an entity, and every link on that page to another page can be considered a relationship between two entities. When you have something like, when you have your knowledge graph already, you can implement the inference side agent by just giving it two very simple tools: read entity and list entities, or page through entities. That's what the list entities tool would do. So, the fact that you can do this with just two tools and that they're really simple is I think, shows that how powerful this method is, given the simplicity. So when you're building the knowledge graph, you can, there's a bunch of tooling available for this, and most of them have you define ahead of time a finite set of explicit relationship types. So like if we were building a knowledge graph about like family trees, for example, you would have to say, something can be a child of, it can be a parent, it can be a grandmother, stuff like that, cousin. But in practice, we found that this is actually more efforts than it's worth, and it's actually very constraining. To have to know about all the possible types of relationships ahead of time, it is useful. Like if you know a lot about your domain and you're sure that there's no side cases, that can totally work. But we found that for most things, it's actually so much more natural for the large language model to just write out the relationships in natural language. And I think this is because they're already trained on things like markdown files and code. They're already trained to navigate those. So this is an example of what we use at Knowledge Work, which is it's actually a much simpler way of doing things. So we've eliminated the tools like add relationship or edit relationship or add statement, and we've thrown that all away and made something much more simple, and we found it actually to be much more performant and powerful, which is just, we have our entity name, and that has to be unique with in a namespace, like in a user's account, for example. And then attached to that entity is a markdown document, which literally resembles like a Wikipedia article. It has in Markdown it has a formatted link that represents the relationship, and that's super powerful because the large language model can say in natural language exactly what that thing is to this entity, and that's extremely powerful because when you're doing inference, it means that these nodes will be extremely dense, and it will reduce the number of hops that are required in order for the large language model to understand everything. So like we found that on average at Knowledge Work, when you ask even a pretty complicated question, we only require about 3 hops on average, 3 tool calls on average to figure out, A, what you meant, what are all the things you referred to, what does that mean to you, and then provide an answer. And that's because we're creating the index, we have the ability to make it really dense and have it, describe the things that it's connected to. So yeah, you might be thinking like, all right, we have this graph which can be extraordinarily complex. Isn't this going to, isn't like the worst case time complexity of this extremely high? And you'd be right. Technically, the worst case time complexity is terrible, and yet Claude Code still works when you ask it to ask questions about your code base. And that's because in the real world, knowledge just turns out to be incredibly dense. So each piece of knowledge is connected to many, many other pieces of knowledge, and you can kind of get a good picture of it by just looking at a few things. And I would equate this to a similar principle to like the 6 degrees of separation to a celebrity phenomenon, or the fact that the statistic with Wikipedia, where every page on Wikipedia you can probably get to every other page, or 94% of pages, with only 3 hops. I don't know if anyone's played this game, but I've played a game where it's a multiplayer game, and you try to see, they give you a random page, and you try to see how quickly someone can get to the specific other page, and it's actually pretty fun. But it's always surprising that people do it in like 30 seconds every time, the people that are good at it. But yeah, that being said, definitely whenever you're doing something like this that is technically the worst case time complexity is pretty bad, you definitely want to set a sensible limit. All the tooling that will allow you to do something with this is will definitely have sensible defaults set. So yeah, why use GraphRag when it's so expensive? It's just the best. It's the highest quality thing. We tried a bunch of things. This is it handles the highest complexity relationships because it's so flexible. The other thing is that this solves a very specific problem that I think is I think it's pretty common, but it's absolutely applicable to knowledge work. When you're on a team and you're constantly making decisions, you're writing new documents. Basically, everything you're doing is kind of invalidating what you used to know. So you've probably at work, you've gone to a document that's only a month old, and you've realized, why is this completely out of date already? So that is, knowledge graphs handle that type of conflicting information very, very gracefully. That works super well. Whereas embeddings, like let's say you were building the type of system that would answer questions about work documents. If you used embeddings for that, you'd be very likely to kind of saturate the most similar chunks for any given query in the past, and then any new document you add would have to compete with those old chunks for similarity. So the embedding system doesn't natively have a good way to handle that. You could do some recency bias thing, but it gets very complicated quickly. Whereas knowledge graphs handle that natively. And then it ends up being surprisingly efficient traversal. So I don't know about you, but when I ask Claude Code a question about my code base, it does 47,000 tool calls. Whereas again, with a knowledge graph, it's so dense and it's constructed just for this purpose. So unless you do it completely wrong, it's going to be much more efficient actually than doing it on natural documents. But yeah, the main drawback is it's expensive. So it's definitely expensive. There's a setup phase. It's way more expensive than embeddings to perform that setup phase. So how do we decide, given all this, these different methods? The kind of easiest consideration at first is how many corpuses of data are you working with? If you only have one kind of set of documents that you're trying to retrieve from, like in the case of a customer service chatbot, for the whole company, there's only 100 max policy documents that you're going to have to chunk and retrieve from. In that type of situation, you can make pretty good assumptions about your data. You can say, oh, it's all formatted in sections, and we can chunk it like this, and you can iterate, knowing that your data is probably not going to change wildly, next month. In that case, embeddings could work pretty well, because you could invest the time to make them work and debug the issues that you're going to run into. But that's most LLM applications. I would say that most LLM applications they have many corpuses. They have one data set per user essentially. So in that case, you can't make as many assumptions about your data, how the chunks should work, and it's going to be very hard for you to iterate and know that you're trying to force a one-size-fits-all solution on everybody's data, which might have different properties to it. So in that case, you should probably use one of the agentic methods. So the other consideration is how much structure is there naturally to the data. So like in the example of code base, there's so much structure because humans need that structure to use it themselves. If that's the case, then agentic traversal without knowledge graphs is a totally probably your best bet. If there's not a lot of structure and there's a very, very high volume of data, you're probably going to have to use embeddings. Because that's the only thing where you can confidently say that you've approximately searched over all the data every time a user makes a query. Versus if you tried to use agentic traversal on something where there's no structure to the data, how is the agent going to find the answer? It'd be very, very difficult. And the last thing is the frequency at which new data is added and if it's possible for new data entries to invalidate old information. So if you're going to constantly be adding new information, like is the case with like a workplace, you're going to be constantly, people are going to be writing new PRDs, TDDs all the time, and every single one of those could possibly invalidate the claims made by earlier documents. That's going to make it really difficult to use an embedding solution. And that's kind of the perfect ideal scenario for a knowledge graph, which handles those, which resolves those information conflicts in the index itself. So yeah, overall comparison, embedding RAG, if you have no money and you have a massive amount of data, like you have absolutely insane data scale, you probably have to use embedding RAG. But again, I never want to use embedding RAG because when you're responsible for a user opens a ticket and says, why did it say this? You're going to have a terrible time explaining that. Agentic traversal, if there's high structure to the data, this is totally an option. That's probably an obvious answer. If there's not obvious structure to the data, and you want the highest possible quality and being able to model the highest complexity relationships, then you probably have to use GraphRag. So practical tips for starting and implementing a system like this. The first thing you should do is manually find whatever, an example of whatever document you foresee being used by the system. So like in the case of the customer service chatbot, manually get the policy document, from HR, put that into ChatGPT and make write an example question about it. And that, this uncovers so many things that you don't think you're gonna run into, but it either uncovers a bunch of problems or it exposes the fact that maybe LLMs actually can't do what you think they can. The other thing that I've seen is when people do this, they're really excited about, oh, I'm going to build all this complex infrastructure and it's going to be so fun. And then if I tell them to try, just try one example of uploading the document to ChatGPT and asking a question about it, you can see that it's not as exciting as you previously thought, and that's a good reason to always do this before you begin a big project. That said, that's not to say that this all is very exciting if it's appropriate. The other big issue that I see people run into is that they don't actually log the real prompt that gets sent to the LLM. There's so many frameworks and like templating languages and ways to put everything in an enterprise environment, package that into the prompt, and then send it to the LLM. And people often think that they're sending one thing to the LLM and they're not, or they've totally forgotten about entire parts of the prompt that are added as part of the this framework that they're using that are ruining everything. And so this I've seen, that's probably the most common problem that I've seen, and I've gone to debug their systems and I'm just like, show me the logs of the prompts. It's amazing how fast you can help people when that's the case. But yeah, if you don't do that, you're very liable to, if you don't log, like for example, the chunks that you're actually sending to the LLM in an embedding retrieval situation, you're going to be so confused when it hallucinates. The last thing is source linking everything, particularly to the logs, but also to any index that you make. So anytime you're ingesting data and you're making embeddings or you're adding to the knowledge graph, you want to make sure that in your database there is a link to the source document that caused you to ingest that. Again, I feel like this should be obvious, but people don't do it for some reason. And specifically for like embedding rags, you don't just want to source link the document, you want to source link the location of the chunk in the document, and that's another thing that people fail to do. It's surprising that you know, maybe like, why would I need to do that? Couldn't I just like Control F the chunk? But usually, you know, you've uploaded like a PDF, or you've uploaded you know, a bunch of different types of things that have turned into text and may not actually be Control F-able. That's the other big problem I've seen is not logging where the chunks are from in the document. So yeah, in summary, use embeddings when you have a stable corpus of data. It's not going to change, and or it's going to change very rarely in a way that you can modulate and roll out. Use embedding RAG when you have extremely large data volume. So at a certain scale, it just becomes impractical to use LLM inference as part of retrieval, but maybe not for long. Use agentic traversal when you have data that is very inherently structured and organized already, and use GraphRag when you don't have data with inherent structure and you potentially have data that is evolving and new data is conflicting with old data. And that is it. Thank you. Hey, do questions?
Yeah.
Questions? Hold on.
Oh, you're gonna do it?
Grab it.
Oh my gosh.
Yeah.
Oh, I guess you too?
Yeah.
Great. Oh, very cool. All right, so just right there in the last part, right, you were talking about having source linking the sources and also the chunks and the traces, etc.
Mm-hmm.
So what are the strategies for when things aren't working? Like, how does that stuff help you? I can understand how it helps you find what the problem is, but how does it help you fix it?
So with embeddings, it's very difficult. You know, the step zero is understand what the output should have been, and that's really hard to do if you can't actually look at the source document. So that's the sole part of that is to you know, can I see the source document? In the source document, can I see, like, usually there's a chunking issue. The heuristic used to chunk has made a weird chunk, or it's cut off the wrong
Right,
thing.
I understand all that for the embeddings and stuff, yeah, but for GraphRag, how does it help you?
So a potential problem.
Solve the problem.
Yeah, so like a potential problem you might have in GraphRag is you might have a statement in your, for example, like what we're using, in your kind of wiki-like markdown document, you might have a statement that is incorrect or is misleading, so that when the LLM reads that statement and tries to respond to the user, they mislead the user as well. So we have to go back in time and figure out why did the LLM write this misleading statement, and the only way we can do that is if we, you know, usually what I've seen is like there's one. Yeah, usually what I've seen is there's, you know, we've ingested a work document, you know, at time 0. It said one thing, and then we ingested a new document, and that document was weird, and our prompt had something in it that conflicted with that or something. So I mean, it's hard to describe this type of problem in general. It's really just kind of just a case by case basis, but it's usually a problem with your prompt. You've made incorrect assumptions in your prompt. But to figure that out, or you've made incorrect assumptions in your prompt, or you've failed to specify exactly what you want in your prompt. I would say that's much more common. People very often write prompts that they think are precise and are actually very vague if you're thinking about it like a computer would. Yeah, sorry, I can't be more specific, but I would have to see your specific error.
Who's next? All right, back there.
Athletes.
So this is a personal question. There is a huge fight in the knowledge graph community. There is guys who say like the old school semantic web people. And
Semantic what?
In the semantic web, where you have very structured like subject, predicate, object graphs.
Yeah, and the relationships.
And there is a new kit that the NumFOCUS basically pushing that say you just create a graph with them. They call it property graph basically.
Yeah.
Any age could be like anything, like what's your personal sort of preference?
Yeah. Oh, if you couldn't tell, I'm definitely in the new kid crowd. It's so in my experience, we started with this immensely complex. We tried to enumerate every type of relationship that you could have between any abstract concept in the workplace. As you can imagine, that just didn't work. There's no way we could possibly describe, how any concept could be related in the workplace. It was very, very abstract, and it didn't work well, and it just cost a bunch of tokens and confusion.
Yeah, but with the old school guide, you don't enumerate every single relationship. You have a type system or class system, right? That
Yeah.
things fall in kind of, or they don't. Because one thing I find that if you show them, like they have some ontologies, the description of relationship, if you show it to LLM, they actually trained on all these formal languages, so they can put the query to the very tight query to the knowledge graph database.
Yeah, so if you, it depends how you want to query the knowledge graph afterwards. So if the knowledge graph that I showed, where it's like the entities are literally markdown documents, that isn't amenable later on to a structured query language. So you totally lose that. I think it's worth it because I'm willing to use an LLM to traverse the graph. It's expensive, but for example, like the other reason why I think this is where things are going is this is how Claude Code works. It's not using a structured language to traverse like the graph that is a code base. It's just understanding the semantic relationships between the things in the code base, on the fly. But I can totally see if you have a domain where these types of relationships are much more structured, then you would totally want to use this structured. You would have it create types and specific structure, subject, predicate. But yeah, when we switched to doing it this way, we use fewer tokens, and we got better results.
Maybe just use voice or something like that. Do you want to? Yeah, if you just speak up.
Okay, so I think you might have covered it, but I have two questions regarding hallucinations. So chunking might help, but if there is a missing information, if I query it, how will it? Would the answer be a hallucinated answer, or it would say I don't know, it's not there in the database?
Yeah, so more and more the models are being trained in a way that allows them to detect when they don't know things. This is not a natural property of LLMs, though. This is a artificially constructed property that the LLMs are spending a lot of money to try and kind of manufacture. So yeah, the hallucination with chunking, I would say it's unavoidable. I would say with no matter how you chunk, you're always going, like the fact that you are not including everything, you're only sending a chunk of what's relevant to the LLM, and you're hoping actually that you actually picked the right chunk. So there's no way around it. You can only do so well. Some people have managed to make really high performant embedding RAG systems. But I think that's kind of a fundamental problem that you can't be 100% sure that you'll fix. So yeah, the hallucination occurs when you've told the LLM, here's the user's query, then you've told the LLM, here is information that contains the answer to the user's query, and it doesn't. So then you've put the LLM in an impossible situation where it has to construct something to appease you. More and more they are figuring out how to reject it, but that's still doesn't solve your problem if you're working in the application layer.
Actually, solution for that, you do the two-step query. So like first one goes to knowledge graph, and then yeah. So I have the exact solution for that. So you first query goes to knowledge graph, that's what it shows, and it has to tell like which query it did and which documents it got. So you got the second call to LLM that basically asks like whatever data that's presented, did it answer the user query? Is there evidence?
Yeah, that's totally a valuable solution. Like there's also you can mix and match everything I just said. it was kind of just an overview. There's so many permutations of approaches here, which is why retrieval, I think, is going to be such a big part of engineering in the future. But like one thing that you can do is if you have you've retrieved 5 chunks, you can ask the LLM, okay, did we, what's the likelihood that we actually got the answer to the user's question? And if not, we can look at more chunks. Like we can agentically decide to make more lookups, or to solve that the problem I described at the beginning, where you have out of context chunks. You have references in chunks to other things in documents that the definition isn't included. We can look up that definition. So there's so much that you can do here, but I will say, if you're going to do stuff like that, I would say why not just use a knowledge graph when you're going to take that cost anyway.
Let's do one more question.
Thank you. I'll ask the question and then later I'll respond to the other piece. The question.
Sebastian.
Thank you. Yes, so the question is, once again, on sort of the ontology and taxonomy piece, which is that if you don't pre-select what kind of entities and relationships should exist in your graph, and you sort of like let the LLM make it up as it goes, you can run into 2 situations. One is like you have different entities being created for the same or similar thing, and the other one is like having in your natural way of having meetings and other stuff, there's like the same word occurs, but it means different things in different contexts.
Yeah.
How do you address that?
Yes, this is a very good question, and this is one of the hardest parts of making a knowledge graph, is the fact that like when you're referring to multiple concepts, where does one thing end and another thing begin? If I have like Massachusetts as an entity, and I observe, I ingest data that talks about Boston, is Boston a different entity, or should I put Boston as an entry into Massachusetts? So all of that has to be articulated in your ingestion prompts. So I'm not suggesting, when I was talking about, we didn't use this very structured ontology where we talked about, we enumerated a finite set of possible entity types and relationship types. We did enumerate we very intricately have decided and iterated on this over time, what exactly constitutes an entity. What should an entity be? What are the possible types of things? And how should the markdown article be formatted? That is very important. I would say it's really reasonable to iterate on that though. So versus like iterating on like embeddings is significantly harder. We found it pretty difficult to iterate on the ontology when there's a finite set of things, because then you have to, like, if you've classified one entity as one thing and you have to migrate to a new ontology, that's very cumbersome. I never want to do that again. But if you make it, just because there's just because we're using this very flexible markdown approach doesn't mean that we don't define the ontology. That's extremely important. I would just say that's something that, like, I can't really tell you ahead of time how to do. Just that, in like kind of like general prompting advice is that the more specific you are, the better it is. And usually it's a matter of I like how you specifically called out letting the LLM decide the details of the ontology. You don't want it to do that. You still need to be in control of the ontology. You need to describe. I care about, so like at knowledge work, we care about whenever there's a person referenced, that's definitely, that's an entity. Whenever there's a project, that is also an entity. Now that one's really, really hard. It's actually really hard to say, like, what, where does one project end, where does the next one begin? Is this part of this project? So that is the hard part about knowledge graphs. But it's totally amenable to iteration.
I also have a very quick comment on the discussion earlier, which is on, like, how do you figure out if your LLM hallucinated, if you actually do like graph RAG or vector-based RAG or anything like that. The newer generations of the SDKs support something called annotations or grounding, depending on which SDK you get different names. And what that does is it places a reference to a previous chunk in your trace into the response of the LLM and tells you which part of the response was based on which part of a previous piece of information in the context or in the trace. What that allows you to do is you can look at all the different parts and say which ones were not cited by something in the context. That part might be made up because the LLM doesn't know where to get that information from. The other parts might still be wrong because the chunk it references doesn't actually contain the answer, so that is still a thing, but at least you know where there's a chance of the LLM making something up completely from scratch. So that might be an interesting thing to look at.
Yeah, I think we're gonna just